Usually when we talk about a medical diagnosis, there's this expectation of absolute precision.
Right, like a yes or no answer.
Exactly. You break your arm, the x-ray shows that jagged white line, and the doctor just points at the screen and says, there it is, broken or not broken. It's clean.
Yeah, totally black and white.
But then you step into the world of physics, specifically relativity and how we actually perceive the universe, and suddenly that x-ray machine is just, well, it's broken. We're looking at a landscape of reality that is incredibly murky.
Oh, it is the absolute definition of diagnostic muddy waters.
Yeah.
Because the tools we use to look at reality, even our own eyes and our fundamental mathematical models, they might actually be distorting the picture from the very start.
So today, our mission for this deep dive is to try and fix that x-ray machine. We're exploring a highly technical, really visually fascinating blog post known as Einstein's Slack 131.
Yeah, and to do this properly, we're going to use the perspective of 3D computer modeling. So think like someone using the software Blender.
Right. We want to uncover some massive potential blind spots in how classical physics handles these thought experiments. Specifically, we're focusing on a huge tension. The difference between Maxwell's electromagnetic field 3D space, which is like the absolute grid.
It's static background of everything, yeah.
Exactly. We're comparing that absolute space to the apparent light rays inside the 3D space of an interferometer inertial frame.
Which is quite a mouthful. But essentially, we're looking at how light rays reach what the author calls a camera eye, like a literal point of existence that receives light.
And we're testing this under two really specific conditions, right?
Yes, exactly. We're looking at when the camera eye has a velocity of 0 in the electromagnetic field.
Yeah.
And then what happens when its velocity is greater than 0 but less than the speed of light, which we call c.
Okay, before we go further, we should probably clarify what an interferometer is, just for anyone who isn't, a physics major.
Good call.
It's essentially an instrument that takes a beam of light, splits it, sends those split beams down different paths, and then bounces them back together.
Right, to measure incredibly tiny differences in things like distance or speed. It relies entirely on the exact timing of how light travels.
And for our purposes today, to make this complex interferometer inertial frame easy to visualize, we're just going to picture it as a giant moving train.
A very specific 3D train.
Yeah, let's unpack the visual setup here. Imagine a giant wireframe cube, 20 units wide, 20 units tall, 20 units deep. This is our train.
And it's sitting in a standard 3D Cartesian coordinate space, an X, Y, and Z axis.
Floor to ceiling, side to side, front to back. Now, to understand the problem the author is pointing out, we have to talk about how we view this space, because there are two ways to look at it.
Right, the mathematician's eye versus the camera eye.
Exactly. Think of the mathematician's eye like a video game developer looking at the game's code. They see every single point in that XYZ grid existing simultaneously. They see the whole map at once.
But the camera eye, that's the player's perspective actually inside the game.
Right. The player only sees what the light engine renders and delivers to their specific location on the map.
That is a crucial distinction. In Maxwell's electromagnetic field, a camera eye is a strictly localized point. Because light actually takes time to travel through the physical field, the eye never actually sees now.
Because it's waiting on the data to arrive.
Exactly. The universe isn't rendering instantly for the camera eye. Instead, I want you to imagine a transparent sphere, say, with a radius of 1 entirely surrounding that camera eye.
Okay, I got the sphere in my head.
Light rays from all over the universe are passing through that transparent sphere simultaneously. Those specific rays are what arrive at the eye at the exact same moment.
So that creates your picture of reality.
Yes, even though those rays might have originated from vastly different places at vastly different times.
Oh, wow. So if I'm looking up at the night sky and a star is a million light years away, but the street lamp down the block is like 30 feet away.
The photons hitting your eye right now are passing through that invisible sphere around your head at the exact same time.
That's wild. Their journeys were completely different. One took a million years, one took a fraction of a nanosecond, but my brain just stitches them together into a single now.
That is exactly how it works. And this brings us to that very first condition, a camera eye with a velocity of 0.
So perfectly still in the absolute field.
Right. Historically, this is how the astronomer Ole Romer mapped the electromagnetic field centuries ago. He essentially treated his observation point, the sun, as a fixed point with a velocity of 0.
And in that stationary setup, light just travels normally.
Yep, it simply travels at a constant speed through the absolute field. It is clean, predictable. Your rendering of the universe is perfectly stable.
But the universe isn't static. I mean, we aren't static. The Earth is hurtling through space right now.
So true.
So let's see what happens when we move from that stationary field into our interferometer inertial frame. Let's get our giant wireframe train moving. We're going to send it rushing forward, slicing through Maxwell's stationary field along the x-axis at 60% the speed of light. So 0.6 c.
And this is exactly where the classical math starts to show some major cracks.
Because the source brings up a historical critique here, right? Regarding the famous Michelson-Morley experiment, specifically Michelson's first attempt back in 1881.
Yes. Michelson assumed that if you fired a beam of light inside a moving train, say a path of length 10, across the Y's plane like from the floor to the ceiling, it would simply travel its normal path.
Just go straight up, hit the ceiling, and bounce back. He was ignoring the fact that the train itself is moving through the absolute electromagnetic field while the light is traveling.
He was completely assuming the light inside the train behaves as if the train is perfectly stationary. But what's fascinating here is the math of apparent speed from the source.
Let's break that math down.
Okay, imagine you're inside that train moving at 0.6 c. If you shine a flashlight straight toward the front wall, the x-axis is, the light is trying to travel forward at 1.0 c.
But the front wall of the train is literally running away from the light beam at 0.6 c.
Exactly. So, to an observer inside the train, the speed of that light rushing toward the front isn't the speed of light at all. It's 1.0 minus 0.6. You are left with the perceived apparent speed of just 0.4 c.
It's like walking on a moving walkway at the airport, but the walkway is moving in the opposite direction. You're walking at your normal pace, but to anyone watching, you are barely inching forward.
That's a perfect way to picture it. Your progress is severely delayed. But what happens if you point that flashlight in a different direction, say straight up at the ceiling?
Right, along the axis.
Here, the geometry gets complicated. The absolute speed of the light flying through the grid of the universe is still 1.0 c. But the train is dragging the starting point horizontally at 0.6 c.
So because the floor of the train is moving forward out from under the light beam, the light can't just go straight up. It has to travel diagonally through the actual electromagnetic field just to hit the spot on the ceiling that's directly above where it started.
Yes. And because it travels that longer diagonal path through the absolute field, its apparent vertical speed inside the train is compromised. Using the Pythagorean theorem, the apparent speed of the light moving from the floor to the ceiling isn't 1.0 c, it's only 0.8 c.
Okay, hold on. I want to make sure I am really visualizing this correctly. If I throw a regular physical baseball in a normal subway car, the ball just moves normally relative to the floor. The air in the car is moving with me. Why doesn't the light just move with the train?
Because light doesn't care about the air in the subway car. Light propagates through the absolute electromagnetic field of the universe.
So the walls of the train are just transparent to the field.
Entirely transparent. Think of it like trying to trace a straight vertical line on a piece of paper, but someone is violently pulling the paper horizontally out from under your pen while you draw.
Oh, wow.
The paper is the field. It doesn't care about the walls of the train. The line you draw on the moving paper is going to be a long diagonal, not a short vertical one.
That makes so much more sense. So, because the train is moving, the light rays inside it are apparent light rays. They're behaving entirely differently than the absolute light rays in Maxwell's field.
Exactly.
So let's test this. Let's see what happens if we try to throw something inside this train. Imagine you, the listener, are standing dead center in this massive wireframe train.
And you have a handful of what the author calls photon balls, essentially little packets of light that you can throw.
Right. You're standing in the middle, and you want to throw these photon balls toward the driver's seat, which is perfectly centered on the front wall 10 units away.
The source text gives us a very specific thought experiment for this. Imagine you throw a whole bunch of these photon balls all at once in a cone shape, aiming toward the driver's cabin.
Okay.
You angle your throws based on those apparent speeds we just talked about. The vertical speed is 0.8, the horizontal speed is 0.6. If you do the math, that means you're throwing this cone of light at an angle of roughly 56.31 degrees.
Okay, so I'm in the middle of the train. I toss a cone of light toward the front wall at a 56-degree angle. If I'm using classical mathematician's eye logic, I'd assume those balls travel 10 units forward, hit the wall, and leave a perfectly neat circular trace on the back of the driver's cabin.
The circle about the size of a hula hoop, right. That is exactly what Michelson would have calculated. Just simple triangles on a static piece of paper.
But the train is moving.
Right. Here is the massive reality of apparent speed. Remember, That front wall is running away from your photon balls. Because you threw them at an angle, the forward component of your throw isn't even that sluggish 0.4 C we calculated earlier.
Wait, it's even slower.
It's a fraction of a fraction. The actual forward speed catching up to the wall is barely 0.36 C. It is crawling.
If the forward speed is crawling that slowly, how long does it take for the light to actually hit the front wall? Classical math assumes it's practically instant.
It takes an incredibly long time to catch up. In the author's exact model, it takes 27.77 seconds.
Wait, really? Almost 28 seconds.
Just imagine that. You throw the light, and you're waiting almost half a minute for it to finally strike the wall 10 units away.
That is a staggering delay.
And it gets worse. During that huge delay, while the light is desperately trying to catch up to the x-axis wall, the z-axis component, the spread of your cone, is still traveling outward at 0.8 C.
Oh no, so it's just expanding.
It just keeps expanding and expanding. So by the time the light finally kisses the front wall nearly 28 seconds later, you don't get a neat little hula hoop circle.
You get a massive circle.
A circle with a radius of 17.728 inside the train. And if you viewed it from the electromagnetic field, the absolute field, it's even larger, 22.16.
It completely misses its intended target. It covers the entire front wall and then some. This completely breaks our intuition of how space inside a moving vehicle should work.
It really does.
The source also mentions tossing a photon ball at a 45-degree angle, right? Does that fix it?
Not at all. It perfectly illustrates the exact same broken logic. If you throw a photon ball at 45 degrees, classical math tells you it should land at a specific height, z equals 14.1.
But the wall is running away.
Yep. The light is delayed by more than 12.5 seconds in that model. So the light just keeps drifting upward. By the time it finally hits the front of the train, it strikes the wall vastly higher than you aimed.
So if the math was off by that much, how did Einstein or Michelson or any of the pioneers of physics not see it? Are we saying they just forgot to account for a moving target?
That is exactly the profound accusation this blog post is making, which transitions us perfectly to the second condition we mentioned earlier, the moving camera eye.
Okay, here's where it gets really interesting. We looked at the camera eye at velocity 0. But what if the camera eye is the one moving through the field?
Right, a velocity greater than 0 but less than c, just like our moving train. Or, frankly, like the Earth moving along its orbit.
So we are the moving camera eye.
Exactly. And the author points to James Bradley, an astronomer in the 1700s, who provided a brilliant insight into this. He was trying to measure distant stars, but he realized that if the Earth is moving, the starlight falling straight down from above is hitting a moving target.
It's like driving a car through a rainstorm. If you're parked, the rain falls straight down on your windshield. But the faster you drive, the rain seems to be coming at you horizontally, directly into the glass.
That is a brilliant analogy. If Earth is moving sideways at 0.6 C, the starlight falling at 1.0 C doesn't appear straight anymore. It creates an apparent diagonal light speed of 1.166 C.
So Bradley had to physically tilt his telescope forward just to catch the starlight down the barrel.
Yes, and that necessary tilt was actually one of the first proofs that Earth was physically moving.
So let's synthesize this grand conclusion the author is driving at, because what we're discussing is highly controversial. The core argument is that when a camera eye is moving, when velocity is between 0 and c, the light it receives is delayed and distorted into these apparent rays.
And the controversial claim is that early physics math ignored this difference. They confused the mathematician's eye, that God's eye view where all 3D points exist simultaneously, with the messy, time-delayed reality of the moving camera eye.
They assumed a static blueprint on a piece of paper was exactly what the observer inside the moving train would experience.
Yes. They assumed if you draw a diagram of an interferometer on paper, the moving observer perceives the light exactly as drawn.
But as we just saw with the photon balls, the massive time delay from apparent speed radically changes the geometry of what actually hits the wall.
Which brings us to Hendrik Lorentz and the Lorentz contraction, the famous idea that moving objects physically shrink in the direction of their motion.
Right. The author has some incredibly strong words about this. They claim the Lorentz contraction was basically just a mathematical patch.
A post hoc trick. Think about the panic these early physicists must have felt. When Michelson couldn't make the math of his moving interferometer match real-world observations, when the light didn't behave like the static paper diagrams, They needed a way to force the equations to balance.
Because math said the light should take 28 seconds and make a giant circle, but they couldn't deal with that.
Exactly. So instead of properly accounting for how delayed light information reaches a moving observer in a 3D space, Lorentz proposed something radical. He said, what if the train itself is shrinking?
Wait, literally shrinking?
Mathematically, yes. If you shrink the physical length of the train in the direction it's moving, then the front wall isn't as far away. If it isn't as far away, the crawling, delayed light beam doesn't have to travel as far to catch up.
Oh, wow. So Lorentz invented length contraction to artificially shorten the distance, forcing the delayed arrival time to look instant.
That's the claim. It was a trick to make Minkowski's space-time diagram work without properly dealing with apparent light rays. It was a failure to separate absolute 3D space from the localized, time-delayed rendering of the observer.
That is mind-bending. But it brings us to the ultimate question. So what does this all mean for you, the person listening to this?
Right. Why does this matter to everyday life?
You might be commuting to work. You aren't doing calculus to figure out how light hits your windshield. Why care about a mathematician's eye versus a camera eye?
It matters deeply because it shows the immense danger of assuming our point of view is an objective map of reality.
The map is not the territory.
Exactly. We build these perfect mathematicians' eyes in our heads. We think we see the whole 3D grid at once. But our perception is always localized. It's always delayed.
And when we hit contradictions in our lives, we end up having to invent complex patches, our own psychological Lorentz contractions, just to explain away the inconsistencies.
We shrink the evidence to fit our predetermined math. We absolutely do.
It's incredible.
And this raises a final thought for you to mull over after this deep dive ends. If physicists had to invent a mathematical patch just to reconcile the delay of light reaching a moving camera eye, it begs a bigger question.
Which is?
When you look up at the night sky, or even across a crowded room while you're walking, your brain is instantly stitching together a seamless picture of now.
Right.
But knowing that every single photon hitting your camera eye is an apparent delayed projection, how much of your everyday reality is actually just an incredibly convincing localized illusion?